whenever you have a bunch of capacitors connected in series, their potential differences must add up to the total potential difference, which is the potential difference of the battery. So if you have all of these connected to a battery, and the battery is 6 volts or 24 volts, whatever it is, the potential differences that show up across the three capacitors must add up to 24 volts, or whatever is the voltage of the battery. What about when you have capacitors connected in parallel? So let's just connect a little battery over here. If you have capacitors connected in parallel, we had mentioned earlier that it's as if each capacitor is independently connected to the battery. And let's say that this is the same 6-volt battery that we had used earlier. So each capacitor is independently connected to the 6-volt battery. Like you can start with this plate of capacitor 1, the top plate of upper plate of capacitor 1, and you can follow the copper wire all the way to the positive terminal of the battery. And if you start with the other plate of capacitor 1, you can again follow the copper wire all the way to the negative terminal of the battery. So you can see that capacitor 1 is directly connected to the battery, and it sees the entire 6 volts. What about capacitor 2? You can do the same thing. You can start with this plate, follow the copper wire all the way up to the positive terminal of the battery, start with the other plate of C2, follow the copper wire all the way up to the negative terminal of the battery. So C1, C2 and C3, all of these are individually connected to the battery. That's what a parallel connection is, right? So all of them, what voltage will each of these see? What is the voltage that will appear across each of these? The answer is they will see the same voltage as the battery. So you can see that the potential difference on all the capacitors is going to be the same when they're connected in parallel. Okay. All right. Now let's talk about capacitors, equivalent capacitance. So when you have several capacitors connected in series or parallel, let's start with series. Sometimes it's useful to just replace these capacitors with one capacitor, and that is called an equivalent capacitance. So let's say I've got a battery like this, and I've connected three capacitors, C1, C2 and C3. Sometimes it might be more convenient to just replace these three capacitors with one capacitor, which does the same thing. It's going to have the same potential difference. So this is called the equivalent capacitance, C equivalent. And you can also do this when you have capacitors connected in parallel. So you've got C1, C2, C3, and these guys are all connected in parallel. So hopefully you can see that this is just a parallel connection. The positive end of the battery is independently connected to the three left ends, and the negative end of the battery is independently connected to the three right ends. So here also you could just have one battery and one capacitor, which is just going to be the equivalent capacitance of these three. So if you have some capacitors connected in series or parallel or both, how do you get the equivalent capacitances? Well, the formula for the equivalent capacitance when the capacitors are connected in series is this one. 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on. So in other words, it's summation 1 over Ci is 1 over C equivalent. So that is the how you get the equivalent capacitance when you have some capacitors connected in series. And what about when capacitors are connected in parallel? So in parallel, the formula for the equivalent capacitance is very simple. It's just C1 plus C2 plus C3. And the proofs of these are really simple. So you can look at the text, look in the textbook, and if you're curious about how to prove these formulas, it's just like 1 or 2 lines of algebra. I'm not going to mention the proofs in this video, but as I said, if you're interested, you can either look in the book, or I'm pretty sure you can figure it out yourself. It's very, very simple. Okay, so we know how to combine capacitors in series and parallel. Okay? So what we have next is a bunch of problems on these concepts. So I think it might be a good idea to um, work through this problem, and I'll let you work out the other ones yourself. Okay, so the potential difference across the 2 points A and B is 25 volts. You have to find the equivalent capacitance of the system between the system of capacitors between A and B. So let's see what we have here. We have three branches, right? So these three branches are parallel to each other. So this is the first branch, this is the second branch, and this is the third branch. You can see that they're parallel to each other. And in the second branch, I've got three capacitors which are in series. So this is a combination of series and parallel connections, right? So we want to replace this whole thing by one capacitor. So how can we do that? So in order to do that, what you want to do is keep simplifying the circuit step by step. So the first thing that we can do to simplify the circuit is maybe combine these three series capacitors in the middle branch and replace them by one. So how would I combine the 18 and the 30 and the 10? I could just do um, so I could replace it. So the new circuit would look like this. There would be the 7.5, and there would just be one capacitor for the middle branch, and then the 6.5. So what would this one capacitor in the middle be? It would be the result of combining the 18 and the 30 and the 10, which are in series. So you would do 1 over C equivalent is equal to 1 over 18 nanofarad plus 1 over 30 nanofarad plus 1 over 10 nanofarad. And you would simplify that and you would get the C equivalent. Okay, so that would be the equivalent capacitance. We have the C equivalent for this middle branch, right? And now we want to find the C equivalent for the parallel combination of 7.5, the C equivalent that we just calculated, and the 6.5. So how do we do that? So these three are in parallel. So to find the equivalent capacitance of these three, you would just add them up according to the formula. And so then your circuit would become really simple. It would just look like this. One equivalent capacitance for the whole thing, and that would, and so this is diagram 1. Hopefully you're clear on how we went to diagram 2. I just combined these three, and that's how we went to diagram 2. And then we collapsed these three capacitors into one, and that's how we got diagram 3, where it's just everything has been just reduced to one capacitance. So in order to get from 2 to 3, you would just do 7.5 plus C equivalent plus 6.5. All right, so how much charge is stored by this combination of capacitors? So to find that, you can just work with the equivalent capacitance that you found, right? You know that Q is equal to CV. Let's say the capacitance of this is C total. So if you use Q equals CV in diagram 3, then you can get the potential difference across our total equivalent capacitance. That's given, it's 25 volts. So this V would be 25 volts, and C would just be C total. And if you multiply these, you would get the total charge that's stored on this entire combination of capacitors. So each of these capacitors will hold some of the charge, but what we just calculated here is the total amount of charge that would be held by all the capacitors in the circuit. Okay, so that's part B. How much charge is stored in the 6.5 nanofarad capacitor? So you know the potential difference across the 6.5 nanofarad capacitor. Can you tell me what is the potential difference across the 6.5 nanofarad capacitor? The answer is it's directly connected to A and B. One end of 6.5 connects to A and the other end of 6.5 connects to B. So it sees the entire potential difference between A and B, and so it's going to be 25 volts. Same for the 7.5 nanofarad capacitor. That also sees the entire 25 volts. The three capacitors which are in series in the middle branch, they would add up to 25 volts, but they don't. They each have potential difference which is smaller than 25 volts, but they would add up to 25 volts because they're in series. So the 6.5 nanofarad capacitor has a potential difference of 25 volts across it. And so how do you find the charge across this capacitor? You would simply multiply, you would simply use this equation Q equals CV. So you would multiply the 6.5 nanofarads by 25 volts, and that would give you the charge in this capacitor. So I did the first three parts, and as you can see, uh, it's not too difficult. Hopefully you can finish the other two parts yourself. So I'll just let you finish the last two parts.